Hello and welcome to another math video. Today we're taking a look at applications of linear equations. We have several different objectives here. We'll try to get to all of those fairly quickly. Here on this slide, looking at translating from words to mathematical expressions. So you can see, of course, the verbal expression over here, and then the mathematical expression. I'm not going to read through all of these. You could, of course, pause and take the time to read through each of those if you want. I will highlight the subtraction and division ones. Those are the problems people tend to struggle with. Again, for example, just these first two with subtraction. 2 less than a number is x minus 2, compared to 2 less a number is 2 minus x. So again, they sound very similar, but you have to be very careful about how you're translating that. Make sure you pay attention to the exact details. Division can be similarly difficult. Of course, the order is important for division. So for example, with that first one there, quotient of 8 and a number, the 8 has to be the numerator and the variable the denominator. And here we've got verbal sentences, actually. So notice these contain the word is. So that means we're going to get an equation when we translate that. So we have twice a number decreased by 3 is 42. So twice the number would be 2x. To decrease it by 3, we subtract 3, and that is 42, so equal to 42. And then we've got the product of a number and 12 decreased by 7 is 105. So product of a number and 12 is 12x. Decrease it by 7, so subtract 7, and then that equals the 105. The quotient of a number and the number plus 4 is 28. So again, notice quotient of a number and the number plus 4. So the second part, the number plus 4, that whole thing is the denominator, and that equals 28. Slightly different example for the next one, the quotient of a number and 4, comma, plus the number is 10. So quotient of a number and 4, x over 4, plus the number, plus x, is 10. So a little bit different translation there, so make sure you pay very close attention to that. Here, just looking at the difference between an expression and an equation. So for this first one, we've got 2 times the sum 3 plus x minus 4x plus 7. So that is just an expression. We don't have an equal sign. If we throw the equal sign in there, equals -1 in this case, what they went with. So then that is an equation. Notice that the expression in the first part, you could simplify that to -2x plus 13. And if you're going to solve this equation, you actually get x equals 7 if you try to solve that equation. Alright, here we're going to take a look at solving a perimeter problem, and we've got some steps for solving an applied problem. The first step, really one of the most important there, read the problem several times if necessary until you understand what is given and what is to be found. I cannot emphasize that one enough. Just the idea that it might take several read-throughs of a word problem to understand what's going on. Focus particularly on figuring out what the given information tells you and what it is you're being asked to find. Step 2, also very important. Assign a variable to represent the unknown value. You can use diagrams or tables in order to help. Actually write down what that variable represents. And if necessary, express any other unknown values in terms of that one variable. Once you've done all that, writing the equation, it's practically written already. So use the variables that you created. You understand how things work together. You should be able to come up with your equation. Then it's just a matter of solving the equation. Make sure you actually answer the question that was asked, not just x equals 2 or whatever you maybe came up with. Actually translate that back to the context of the question. Does it seem reasonable? And then check to make sure the answer, check the answer in the words of the original problem, make sure that actually works out. So we've got 2 examples here. The first one, length of a rectangle is 1 centimeter more than twice the width. The perimeter of the rectangle is 110 centimeters. Find the length and width of the rectangle. So we've got a couple different pieces of information there. The length is 1 centimeter more than twice the width. Now this is a fairly common situation we're dealing with here. So we actually have a formula that we can use. The perimeter of a rectangle equals 2 times the length plus 2 times the width. So as far as assigning variables and writing an equation, we all understand hopefully P is for the perimeter, L is for the length, W is for the width. It may help to actually draw the rectangle. And again, what they say is the length is 1 centimeter more than twice the width. So if this is the width, because the length is the longer one, the length is 1 centimeter more than twice the width. So length would be 2W plus 1. So we have really all of the dimensions of that rectangle defined in terms of the width at this point. And of course we know the perimeter itself is 110, and so we can plug all that into our equation. So we get 110 equals 2 times the length, but the length is 2W plus 1 plus the width, which is just the width. Now from here again we just have to solve this equation, make sure that we actually answer the question that they're asking, which is they want us to find the length and width of the rectangle. Let's see, so we would want to distribute the 2 into those parentheses. We get 4W plus 2, oops, I forgot my 2 here, plus 2W, and again that 2 is just there because it's in the formula. So we get a total of 6W plus 2, so we would subtract the 2 from both sides. We get 108 equals 6W. We would divide 108 by 6 in order to find the width, and we get a width of 18. Now, so we found the width, but we need to find the length. The length is 2 times the width plus 1. So length is 2 times 18 plus 1. So that would be 36 plus 1, in other words, 37. So really we've answered the question, what is the length and the width? So length is 37, width is 18. And again, you can double check that in the original question, make sure that that actually gives you a perimeter of 110 to answer that actual question, have that work out. The second problem on this page, you can go ahead and try that on your own while you're working on that. If you just want to pause the video and then resume when you're finished, and I'll go ahead and go through that one. Okay, so we've got the John Hancock Center in Chicago. It's got a rectangular base. The length of the base measures 65 feet less than twice the width. The perimeter of the base is 860 feet. What are the dimensions of the base? Okay, so talking about the base is down here. Now they do have some information up here that we are not going to use. We're just looking at the information for the base. So very similar to the one we just did. The length is 65 feet less than twice the width. So we could plug in our 860, and that's going to equal 2 times the length, which is 2W minus 65, plus 2 times the width. So we would want to simplify that. I'm going to drag this slide up a little bit so I've got some room. So we would distribute the 2. When we do that, we get 4W minus 130 plus the 2W, and that gives us 6W plus 130. And so from there we would subtract the 130 from both sides of that equation, which would give us 730. I'll just move over here, equals 6W. Now at this point we would divide both sides by 6. So 730 ends up being, oh sorry, my mistake. Okay, so I knew something seemed off. This is a minus sign. I thought it was plus because it ran into the 1. Okay, so this is really minus 130. So I would add the 130, so this would really be 990. That seemed like it was a bit off. So dividing 990 by 6, so I get 165 equals the width. So if the width is 165, I can use that in order to find the length. So in order to do that, the length is 2 times the width minus 65. Now make sure you follow order of operations. You have to multiply first. So when we do that, we get 330 minus the 165. And again, once we do that, then that will tell us the second part. Oh, of course, I should have figured that. That's 165. So length of 165 and width of 165. Except that's not right either. You're not subtracting 165, you're subtracting 65. Boy, I'm just full of wonderful mistakes here. So yeah, that did not seem right, which is good. Again, I was thinking about the actual question and did not seem to make sense. So caught that mistake there, which is what really matters, right? So the length is 265, the width is 165. Of course, these are in feet. I guess I haven't been focusing on units. Of course, we should. This one being in feet and then the previous one being centimeters. So it does make a difference, obviously, what the units are there. You would hate to say that the base of the John Hancock Center had a length of 265 centimeters. Again, not the biggest deal, but we should make sure that we do use units there. All right, so here we have a couple more word problems. First one, a little bit about baseball. Hopefully you're familiar enough where this will make sense. So back in 2004, 2 pitchers that were pretty successful were Randy Johnson and Johan Santana. They had a combined total of 555 strikeouts. Johnson had 25 more strikeouts than Santana. Now what I'm going to do is I'm just going to have X be the number of strikeouts for Randy Johnson and Y be the strikeouts for Johan Santana. Their names unfortunately don't translate well to different letters because of the similarities there. So I'll just use X and Y. So Johnson had 25 more strikeouts than Santana. So that means if we wanted to find Johnson's strikeouts, X, we would take Santana's strikeouts, Y, and add 25 to that. So we can write X in terms of Y, and we would know, of course, that the sum of the two would be 555. Oops, that's supposed to be an X plus a Y. Is 555. And then just replace the X with Y plus 25. So we have Y plus 25 plus another Y equals 555. Now that's getting strangely close to solving a system of equations using substitution, but that's perfectly fine. When we simplify the left side, of course, we get 2Y plus 25 equals 555, and that's a Y there, just emphasize that. Now it's a funny looking Y. From there we would just subtract 25 from both sides of that equation, so we get 2Y equals 530. Divide both sides of that equation by 2, and we get Y equals 265. Now this is why we want to make sure we define our variables. So we said that Y was number of strikeouts for Johan Santana. So he had 265. And then Johnson would have y plus 25. So if we know y is 265, we can plug that in there. So the 265 plus 25 would give the strikeouts for Randy Johnson. Now really we should write that in terms of the actual context. I'm a little bit short on room to write that down, and you can hear me just fine. So what we're looking at there is Randy Johnson had 290 strikeouts, Johan Santana had 265 strikeouts. That's really how we would answer that question. The next one, very similar. Again, you can give that one a shot. While you're working on that, go ahead and pause it. When you're done, unpause it, and you'll see me go through this problem as well. Okay, so we've got two companies with top revenues in the Fortune 500 list for 2008 were ExxonMobil and Walmart. Their revenues together totaled $849 billion. Walmart revenues were $37 billion less than ExxonMobil revenues. What were the revenues of each corporation? So again, I might just define my variables. This one works a little bit easier. I might just call ExxonMobil E and Walmart W. So we know together E plus W equaled $849 billion in revenue. And we know Walmart revenues were $37 billion less than ExxonMobil. So to get Walmart, you could start with ExxonMobil and then take away $37 billion. So we know W is the same as E minus 37. So again, really it's basically a substitution, although we haven't talked about substitution yet. But we get the equation E plus E minus 37 equals 849. So not too difficult to solve that one. We simplify it, we get 2e minus 37 equals 849. Since we're subtracting 37 from the left side, or it's 2e minus 37, then we would add 37 to both sides. So we get 2e equals 886. And so we would divide both sides by 2. So ExxonMobil revenue was $443 billion. And so then we could figure out Walmart was ExxonMobil minus 37. So W equals 443 minus 37. So their revenue for that year was $406 billion. So here we're looking at solving a percent problem. Information we've got is that in 2002 there were 301 long-distance area codes in the United States. That's an increase of 250% over the number when the area code plan originated in 1947. We want to find out how many area codes there were in 1947. So one, again, tip with this kind of a problem is have your variable be the number you are trying to find. So I have x equal to area codes in 1947. Now, there's a couple different ways to think about this. I'm just going to present one here. So the 301 was an increase of 250% over the number when the area code plan originated in 1947. So we'd have the original number plus 250%. Now 250% is really 2.5 times, would be 2.5. So x plus 2.5x would equal the amount of long distance area codes in 2002, which was 301. So really we put those together, we get 3.5x equals 301, and we would divide both sides of that equation by the 3.5, and we get 86. So x equals 86. Now, Again, we can check to see that this is reasonable. It is a whole number, so yes, that would make sense. You couldn't have 86.5 area codes. You would either have 86 or 87 or 88. The answer has to be a whole number. So the fact that it is a whole number seems reasonable. And again, we could go back and we could check that out and say, okay, well, if it was 86 in 1947, then what would be, again, the 250% increase over that? So that's how we do that one. Again, same sort of problem for 45. You can go ahead and try that one, and while you're working on that one, just pause. Then when you resume, I'll go ahead and go through that one as well. Alright, so looking at 45 there, it was for information's for 2005, talking about the traditional Thanksgiving dinner for 10. Got turkey, stuffing, cranberries, pumpkin pie. Trimmings was $36.78, an increase of 3.1% over the cost in 2004. What was the cost to the nearest cent in 2004? So again, same kind of thing. I would have X equal the cost in 2004. That was only a 3.1% increase over the cost in 2004. So X plus, now be careful with the percentage there. It's only 3.1, so it's 0.031X. And that would equal the 36.78. So 36.78 there. Now you might look at that and say, well, geez, why don't you just go straight to the 1.031X? And if you see that, go ahead and go for it. That's perfectly fine. And all we have to do then is divide the 36.78 by 1.031, and that'll give us the cost for 2004. Now, this doesn't work out as nicely as the previous one. That's because, again, we're doing averages, kind of making some approximations and some assumptions and all that good stuff. So it's not as exact as the area code problem. So you do get a messy decimal. To the nearest cent, it's $35.67. As far as whether or not that's reasonable, it's reasonable because it is less than the 36.78. Again, it increased from 2004 to 2005. So if it somehow turned out to not be less, that would be a problem. But yeah, certainly looks reasonable. You can kind of plug it back into the original, make sure that it does actually translate to making sense for that. All right, here we're looking at an investment problem. And this isn't quite how it would work in, reality, but it does make for a good question. So we've got Mark here. He has $40,000 to invest. He's going to put part into an account paying 4% interest, the rest into stocks paying 6% interest. Accountant says, well, you should get $2,040 per year in income from those investments. The question is, well, then, if that's the case, then what is he investing at each rate? Again, one way to kind of think of this is kind of as if you were looking at a system of equations, or you can just kind of write one in terms of the other. So, for example, if we say that we're going to have, for example, X equal the amount that is invested at the 4%, then the amount invested at the 6% would be 40,000 minus the X. Whatever you don't invest in X, you're going to, at the 4%, you're going to invest at the 6%. So, for example, if you invest 10,000 at 4%, you would invest the other 30 at 6%. So we know that as far as that investment goes, that's what those values would look like. And again, we know that the income will be $2,040. So however much he invests at 4%, you multiply that amount by 4% to figure out the amount of income for 1 year. Again, it's kind of an application of that simple interest formula, principal times rate times time. But here we're looking at a time of 1 year, so the 1 year doesn't really show up in the formula. Now we also want to add to that the amount of money earned from the money invested at the 6% interest rate. And like I said, since there's 40,000 to invest, however much you invest at the 4%, you take that away from the 40,000 in order to get the amount invested at 6%. And accountant says, well, the way I ran it up with the amounts I came up with, you'd get $2,040 per year, so set it equal to 2,040. Now this does give us an equation to solve. We have looked at equations with decimals before, and actually very similar to this, and we looked at multiplying both sides of the equation by 100. Now I go back and forth as far as which way I prefer. With these ones, I find that it usually works out fairly well because, for example, like the 6% of the 40,000 is actually not a bad number. It's 2,400, so it's not too bad if you just deal with the decimals. So you can multiply both sides by 100 if you want, or you can deal with the decimals. I'm not going to worry too much about it. I'm going to show without multiplying in this case. So you get 0.04x plus the 0.06 times the 4,000, like I said, is 2,400 minus the 0.06x, and that's going to equal 2,040. Now, one thing I did forget is that if you actually if you have the bigger interest rate be the variable, then the positives and negatives work out a little bit nicer. So I'm going to have to deal with some negatives here. If I can combine the terms on the left, I actually get negative 2% x plus the 2,400 equals the 2,040. And from there I would subtract the 2,400 from both sides of the equation. So again, that will also be negative. But the fact that they're both negative means that the answer will end up being positive. Like I said, I forgot that little trick that if you actually make the larger percentage be the variable, then things turn out positive, which of course is nice. From there we just divide the negative 360 by the negative 0.02, and we get 18,000 for x. So again, that would be $18,000 at the 4%. And then all we do is we do 40,000 minus the 18,000 in order to get the money at 6%. So there we're looking at 22,000. So 22,000 at 6% and 18,000 at the 4%. And so that's what we're looking at for that one. Again, number 49 here, same kind of setup. You can give it a shot. They do have a table there for kind of holding information. That is a very good way to start getting used to this. Again, I tried my best to explain this one as I went through it, but it is kind of a special setup. We will do plenty of these though, so you can kind of get used to the pattern, but at first it might be a good idea to use that table in order to organize your information. So if you want to go ahead and pause and work through it, I'll go ahead and show what information goes where on this table. Alright, so we got Carter. He's got $12,000 from giving tennis lessons. He invested part of the money at 3% simple interest and the rest at 4% interest. In 1 year, he earned a total of $440 in interest. How much did he invest at each rate? Now notice here they didn't use my trick either. They went ahead and they had X be the smaller percentage. But it's fine. Again, it works. Just, again, not going to be nice and neat for us. But again, the negatives, we can deal with negatives. So as far as the principal goes then, so the amount invested at 4% would be 12,000 minus X. The interest then at 3% would be 0.03x, and at the interest at 4% would be 0.04 times the 12,000 minus x. Try to sneak that in there at the edge of the screen. Hopefully you can see that all right. Now the total principal is the 12,000. Again, you can add the two terms in that column together to get that. And then the total interest was 440. Notice they don't have the rate overall for the two together, so that's perfectly fine. It doesn't really make sense to have that in the table. But really then this right side is the formula that we will use, and I'll just put that along the bottom here. So the 0.03x plus the 0.04 times the 12,000 minus x will equal the 440. And again, you could go ahead and multiply both sides by 100 here. Maybe I'll just go ahead and do that this way this time around. Again, because the numbers work out nicely, we end up getting again some nice values there. So let's see. So we would have, if we multiply both sides of the equation by 100, we get 3x plus 4 times the 12,000 minus the x, and that would equal 44,000. So again, it kind of knocks out those decimals, makes those a little bit easier to handle. We would have to distribute the 4, so we would have 3x plus 48,000 minus 4x equals 44,000. Now I'm running a little bit short on space, so I'm just going to do two things at once here. I'm going to combine the x's on the left and subtract the 48,000 from both sides. So negative x would equal negative 4,000, because 44,000 minus 48,000 would be negative 4,000. And then this one works out pretty easily as far as x equals 4,000. Now remember, going back to our table, x was the amount invested at 3%, so $4,000 at 3%, and then the rest of it, which would be at 4%, would be 12,000 minus 4,000, so $8,000 at 4%. And I'm not going to bother writing $4,000 at 3%. You heard me say it. So, but again, that's what we're looking at there. Again, we'll do plenty of these. But one of the biggest things is kind of keeping track of where all that information goes and using this format. All right, so here's another difficult question. We've got a mixture problem. So we've got a chemist must mix 8 liters of a 40% acid solution with some 70% solution to get a 50% solution. The question, how much of the 70% solution should be used? I would highly recommend at least the table in doing that, if not the table and the drawing. So what we see here is we've got 8 liters of a 40% solution. We've got enough 70% solution to do whatever we need to do. So we're going to add some of that to the 8 liters. And we want the end result to be a 50% solution. Again, we have 8 liters of the 40%. We don't know how many liters of the 70% we're going to use, so we'll call that X liters. So what happens then is when we mix those together, we've got 8 plus X, or really X plus 8 liters of what ends up being a 50% solution. So what we have is really the strengths of the different solutions. So we've got the 40% strong. We know that that's 8 liters. So really that's 3.2 liters of pure acid. And so that's important. We don't know how many liters of the 70%. So X times the 0.7. So again, we don't have a number there, but we have an expression that we can use. But we do know that the end result should be 50% strong. So whatever that X plus 8 total is, for example, say X were 2, we'd have 10 liters. We'd know we'd want half acid, so out of the 10 it would be 5. So 50% of 8 plus 2 would be 5. But again, we don't know because of that X there what it's going to take. So this right column is really the equation that we have. So filling in that table with the appropriate information can be very helpful. And I'm going to even jump right in there with the 3.2. Again, we already figured out what the 40% of 8 is. So 3.2 plus the 0.7, I'm just going to go I'll go 0.70 just to emphasize the 70%. And then I mess up my x there, but 0.70x. And that's going to equal 0.50. And I'm going to go x plus 8. I think they probably went 8 plus x because you're adding the x to the 8, not the other way around, but x plus 8 just sounds better to me. Now from here it's just an equation to solve. So again, we kind of get the pattern down and figure out what we're doing. Again, what we're looking at there is this is how much pure acid we have from the 8 liters of the 40%. We know that's 3.2 liters of acid. We're going to add to that some 70% strong acid. We don't know how much. We want those two together to be 50% strong. Well, if it's 50% strong of x plus 8 liters, then we'd have 0.5 times whatever that total is. So again, now we're just solving this equation. So nothing really to be done on the left side at this point. So we would distribute the 0.5 on the right. I'm just going to write 1/2 x because that's the same as 0.5x, and it's just a little bit easier for me to write that. So 1/2 x plus the 4. Again, I'm going to probably think of it as 0.5 though. I would like the x's to be positive, so I'll subtract the 0.5x from both sides. That was a bad 5. So subtract the 0.5x from both sides. So my x's are going to be on the left, so I'm going to go ahead and subtract the 3.2 just because, again, I'm running out of space a little bit here. So now be careful with the decimals. 0.7 minus 0.5 would be 0.2 or 0.20. 4 minus 3.2 would be 0.8. And then just divide the 0.8 by the 0.2. Again, be careful with dividing decimals. We find out that x equals 4. Again, that doesn't actually answer the question. What we should say is that we should use 4 liters of the 70% solution. I'm just going to pull this up a little bit here, maybe zoom out a little bit, give myself some space. So x should equal 4 liters of the 70% solution. Now, check to make sure that makes sense. If we have 4 liters, that would be a total of 12 liters. Half of 12 is 6, so we should have 6 liters of actual acid. The 8 liters of 40% gives us 3.2 liters of acid, and 4 liters of 70% would give you 2.8 liters of acid. 3.2 plus 2.8 is 6, which of course is half of 12, so the numbers make sense and they all add up. Alright, so again, give number 55 a shot there. They've even got most of the stuff already in the table. You just have, 4 spots to fill in. And again, remember the equation is going to come from that column really, just like it did in the previous example. So give that one a shot. While you're working on that, go ahead and pause, and then resume when you're finished, and I'll go ahead and go through that as well. Okay, so let's see. So 4% of 10, that would just be 0.4. So let me see. I'm going to go 0.4. Just figure that out. 10% of x is 0.10 or just 0.1x. Now this would be x plus 10, and so we get 6% times the x plus 10, like that. And again, so it's a little bit different deal. It's still mixing acid. It feels a little different with the smaller percentages, and actually, I'm sure you caught this already, but it shouldn't be 0.4. That would be 40, or sorry. I got to thinking wrong. So yeah, it's 0.4 because it's 0.04 times 10. So it's actually 0.4 liters of the acid. So again, this gives me the equation. So I've got the 0.1x plus the 0.4 liters of acid that we already have, and that should equal 6% of whatever we get as far as the x plus 10. And again, they might think of it as the 10 plus x because we're adding to the 10 liters that we already have. So we would distribute on the right-hand side. So we get 0.1x plus the 0.4 equals 0.06x plus, and we just multiply that by 10, so that's going to be 0.6 as well. Now, again, we could have multiplied by, say, 100 to get rid of all of those decimals. Obviously, you don't have to. We can deal with them like I am here. From here, again, it gets a little bit weird with this one because of the fact that now we've got a 0.06 and a 0.1. So it's like a 10. So again, one thing you can do there is you can emphasize that this is really like a 10, or 0.10. So subtract the 0.06 from that. So we get 0.4x. Or sorry, 0.04. Let me rewind that a little bit. So 0.04. See, I told you it was tough. So 0.04x. And again, if you're not sure, calculator's really good with that kind of stuff. And then subtracting the 0.4 from the 0.6 would be 0.2. And then we divide the 0.2 by 0.04, and we get 5. So again, what we're saying is 5 liters of the 10% solution. And again, make sure that that makes sense. So 5 liters would give us a total of 15 liters. 6% of 15 is 0.9 liters, so 9/10 of a liter. If we had 5 liters, 10% of that would be 0.5. 0.5 and 0.4 together makes 0.9, so those numbers do add up. All right, we are finally to the last slide of what's turned out to be a long video, so thanks for sticking with me here. These I find actually be almost a little easier than the previous one because we're talking 100% pure stuff. So for number 8, we've got octane rating of gasoline as a measure of its anti-knock qualities. For standard fuel, the octane rating is the percent of isooctane. How many liters of pure isooctane should be mixed with 200 liters of 94% isooctane, referred to as 94-octane, to get a mixture that is 98% isooctane? So again, you could make that table, or maybe you're kind of getting used to these and how they work out. So we would have, again, what we already have is we already have 200 liters of 94% isooctane. We're going to add to that some pure isooctane. So I'm just going to call that X. And since it's pure, it gets multiplied by 100%, but 100% is 1, so I just do 1x. And we want that to equal 98%. So 98%, and as far as how much we're going to end up with, it's going to be 200 liters plus however many liters we add of the pure stuff. And so it would look like this. Again, you could multiply by 100, being that the 94% of 200 and 98% of 200 work out to be such nice numbers, I'm not going to bother with that. So I would just use the decimals. So we get 188 plus x equals 196 plus 0.98x. Now the x's do get a little bit weird, but we would subtract the 188, which I know I just did that in a weird order, but I did that because I want to subtract the 0.98x from both sides. So this ends up being 0.02x equals 196 minus 188. It's just 8. So divide the 8 by 0.02, and we get 400. So So 400 liters of the pure stuff in order to make that work out. Now again, does that make sense? Well, so if we did that, we would have 600 liters, and 600 liters of 98 octane, we would do 0.98 times 600, which would be 588 liters of, isooctane. And of course the 400 would be pure, so that takes care of the 400 already. And the 188 plus the 400 would be 588. So that stuff does all add up. Like we've been doing, the next problem with the dye is same basic idea, although we're talking about dye instead of gasoline. Let's go ahead and try to set that one up. So while you're working on that, just go ahead and pause, and then I will, resume when you're done, and I'll go through that as well. Alright, so how much pure dye must be added to 4 gallons of a 25% dye solution to increase the solution to 40%? And of course, pure dye is 100% dye. So what we have already, we have 4 gallons of a 25% solution. So we would do 0.25 times 4, which of course is going to be 1, plus 100%, or 1, times the x, which we're going to add the pure dye. And we want that to be a 40% solution, so 0.4 or 0.40 if you wanted, times the total amount, which again we don't know, but we do know it's going to be x gallons over 4. So 4 plus the x. Again, we would simplify both sides. 25% of 4 is 1, so 1 plus x equals 0.4 times 4 turns out to be 1.6 plus 0.4x. So I would subtract the 0.4x from both sides. And again, you could multiply by 10 if you wanted to get rid of the decimals. Not entirely necessary, but if that makes it easier for you to think of what's going on, that's perfectly fine. Since I'm putting the x's on the left, I'm just going to go ahead and move all the numbers over to the right, so I'm going to subtract 1 from both sides. Again, if the decimals are a little tricky, use the calculator to help. So that's 0.6x equals 0.6. Divide by the 0.6, you should get 1. So it looks like 1 gallon of 100% dye, or pure dye. Again, does that make sense? Well, if we add 1 gallon, we'd have a total of 5. 40% of 5 is 2, so we want 2 gallons. Well, again, we get 1 gallon of pure dye from the 4 gallons of 25% dye, and then of course we get 1 gallon of dye from the 1 gallon of 100% dye, so that does add up again. As always, thank you for watching, especially with this one, which got to be a bit long, but hopefully you found this to be helpful.